Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello and welcome everyone. It's my pleasure to introduce Roy Schwartz from Technion. Roy is a PhD student of Sefi Naur, who's a frequent visitor here. And Roy is going to tell us about how to maximize submodular functions using continuous methods.
So hi, thank you all for coming. So we're going to talk about submodular maximization today, or more precisely, how to use continuous methods. So this talk will have 3 parts. In the first part, we're going to recall what the submodular function is and also see a few interesting submodular optimization problems. In the second part, we're going to discuss what is perhaps one of the most basic submodular optimization problems, which is the unconstrained submodular maximization problem. And we'll actually see how to get tight results for this problem. And if time permits, in the last part, so the time we'll see how much time we'll have to discuss whether in depth or not. In the third part, we're going to see how to compute good fractional solutions to submodular optimization problems. Of course, if there are questions or remarks on everything, feel free to stop me at any time. So let's start with the introduction. So what is a submodular function? So we have a ground set n, and we have a set function defined over all subsets of elements. And the function is submodular if for every 2 subsets, the value of the union plus the value of the intersection is upper bounded by the values of the subsets themselves. So this is the formal definition. The problem is that this definition is not always so intuitive or not so easy to use. Luckily, there's an equivalent definition which is much more intuitive, and it uses what is called decreasing marginals. So what is a marginal of a set? So if you have a set A and an element U, the marginal value of the element is just the change in the value of the function once you add the element to the subset. As you can see here, the change in the value of the function. So what is the decreasing marginals property? It means that if you take 2 subsets, A and B, and A is not only smaller, but it is actually contained inside of B, then the marginal value of any element that doesn't belong to both is larger with the smaller subset. So this is exactly what is written here. In economics, this property is also known as diminishing returns. So this definition is usually much more intuitive and more convenient to use, and it is equivalent to the first definition I gave. And the last definition we'll need in this talk is that of monotonicity. So formally it means that if you have 2 subsets, again, and A is contained inside of B, the value of A is not larger than the value of B. Intuitively, it means that if you have a subset and you start adding elements, you cannot lose. You only gain more. So either you stay the same or you gain more, and this is essentially what monotonicity means. So notice that it is also, the relation here is inclusion. So let's see a few examples of well-known submodular functions. So this is the first example. We have all these blue points, and the elements of the ground set are actually subsets of points. So you see all these subsets, and the function is the number of points you've covered. So let's say we choose, so let's see that this function, for example, has the diminishing returns property. So we'll see this by example, of course. So let's say we choose this element, an element in the ground set, and we add to it this element. So what is the change in the value of the function? It's all the dark points, because we just count the number of points we've covered. So now let's choose a larger subset of elements in the ground set. Let's say we choose these 2. And now we add, again, the same element in the ground set, this element. And you can see that the change in the function is smaller here. And you can see that actually you gain only a subset of the points you gained before. So this is an example why this function, which is called the covering function, has the diminishing returns property. So you probably believe me if it works for any subset of elements in the ground set. And this function is also monotone. The more elements you choose, the more points you cover. The second example is also quite known, is the cut function in undirected graphs. So the ground set in this case are the vertices of the graph, and the function is just given a subset of vertices, which is a cut, count the number of edges that cross the cut. So let's say we have two cuts here, or subsets of elements. A is the smaller one and is contained inside B, which is the larger one. And now let's see what happens once we add a vertex V. So what happens when we add vertex V to the smaller cut A? So we lose all the dashed edges, right? And we gain all the bold edges, all these edges. So this is the change in the value of the function. What happens when we take the same vertex and add it to the larger cut? So again, if we look at the dashed edges, we lose the same edges we lost before and possibly more. And we gain only a subset of the edges we have gained before. So the change is smaller and also possibly negative. So again, this means that this function has diminishing returns property, so it is submodular. But this function, as opposed to the first function, is not necessarily monotone. So this is an example for a non-monotone submodular function. So these are just two examples. So where else can you find the submodular functions? So as we said, we have covering functions, cuts in undirected graphs. This also works for directed graphs, hypergraphs. Also, the rank functions of matroids are submodular functions. And these are quite classical examples in combinatorial optimization. Also, you can find submodular functions in economics or game theory, usually as utility functions. I might mention a few examples of this talk, depending on how the time goes by. This is where you can find submodular functions. So let's look at the basic submodular maximization problem. So all you have is just a family M of feasible subsets, and you want to maximize a submodular function over all feasible solutions. So this is a very basic problem. An obvious question before we start looking at specific cases of this problem is, how is F given? So note that if F is given explicitly, so if you have a list of all possible subsets and their values, this problem is trivial, assuming that you can check feasibility efficiently, right? Just go over all subsets in the list you're given, check feasibility, and you're done. Unfortunately, this is not very realistic in, let's say, all or almost all the applications of this problem. So what is usually assumed is that the function is accessed through an oracle. So in the most basic oracle that is widely accepted and widely used is what is called a value oracle. So it means that the algorithm has a black box access to some oracle that it gives it some subset of elements S, and it just receives the value of the function of this subset. So this is the only way the algorithm can interact with the submodular function. So now let's go over a few interesting submodular maximization problems. So as I mentioned, this is perhaps one of the most basic submodular optimization problems. So, and it is the unconstrained submodular maximization problem. So you get a submodular function f, which is not necessarily monotone, and just find the best subset. There's no restriction, no constraint. Actually, any solution is feasible. Of course, this function, if it's monotone, then the problem is trivial. So you have this huge ground set, and just find anything that has a good value or the highest value. So why is this problem interesting at all? So from a combinatorial point of view, it captures, for example, Max-DiCut, just to the ground set as the vertices of the graph, and the function is the cut function. And of course, any cut is feasible, and you want the largest cut. So this works also not only for Max-DiCut, but also for Max-directed cut, and it captures also maximum facility location and even a few variants of Max-SAT. So this is from a combinatorial point of view. Also, apparently, this problem is quite useful in other settings, most of them usually in game theory or economics. So I won't go over the entire list, but for example, it has been used on what is called marketing over social networks, when you want to find a strategy to sell things in a social network, or even the most basic scenario when you want to maximize some utility over a discrete choice. So usually in economics, utilities have...
Typically monotone in the examples from economics?
No. And even if it's monotone and it's unconstrained, then just choose everything. So in these problems, the objective is not always monotone. There are examples. And also in some of these works, they actually say if we have an alpha approximation for the unconstrained submodular maximization, this implies some function of alpha approximation for our problem. So in some of these cases, it is even used as the approximation algorithm for the submodular problem is used as a black box, essentially. For example, in these two works, it is mentioned. So this is just a partial list, and it's supposed to convince you that this problem is interesting. So what is known about this problem? So apparently it was studied quite a lot in the operations research community, and this is just a partial list. The only problem is that all these works are not rigorous in the sense that either they examine a very specific submodular function, or they give some heuristics that converge quickly, but there's no proof on the value of the output, or there are algorithms that actually compute the exact optimum, but you can't, of course, bound their running time. So in some of these works use integer programming or mixed linear integer programming, and also all other NP-hard problems, essentially, because this problem is hard. It captures Max-DiCut. So the first rigorous study of this problem was done by Feige et al., and they actually give 3 algorithms. So I'll just go quickly over them. So the first algorithm they give is quite simple. It just says pick a random subset. The surprising thing is that you can get 1/4 approximation for this. So note that if you pick a random subset, this is exactly the approximation you get in the maximum directed cut case, right? Random cut in maximum directed cut gives you 1/4 approximation. And the amazing thing is that this works for a general submodular function, not necessarily just in the maximum directed cut setting. And in that paper, they also improved this and showed that if you do local search, you can get 1/3. And if you also tweak the local search a little bit and change its objective, this is what is called non-oblivious local search, you can get up to 0.4. So this was the case until in SODA 11, Goran and Vondrak actually showed that you can squeeze even a little bit more by the simulated annealing technique. And the remarkable thing is that they actually were able to prove something. Usually simulated annealing is used as a heuristic. So in this case, so I didn't explain exactly how the objective here is defined, but it is defined using some probability and noise. And they showed that once this local search gets stuck, just decrease the amount of noise and continue the same the 0.4 algorithm. And they were able to prove that you can get 0.41. And after that, we were able to squeeze a little bit more using what is called structural tools. Because of time constraints, I won't go into this thing in this talk. And the obvious question is, what is the hardness? How high can you get, or how low can you get? So there's an absolute 1/2 hardness. So what do I mean by absolute? So this is unconditional. So they actually prove that any algorithm for any fixed epsilon that gets 1/2 plus epsilon approximation needs to access the oracle an exponential number of times. So even if in the worst case p equals np, this hardness still holds. In the worst case, so I don't know. Depends on which side you are. An obvious question is, what is the right answer? So here it's nice, but you start squeezing things, and these are ugly numbers, and the proofs and the
Diminishing returns.
Yeah, diminishing returns, and the algorithms gets more and more complicated, and also the analysis and so on. So the obvious question, because 1/2 is a nice number, is it the right answer? And what we will see in this talk, that yes, this is the right answer. And not only is it the right answer, you can actually get a tight algorithm which runs in linear time. It's extremely simple and actually simplifies all these, except this algorithm is also quite simple. But all these other algorithms, it's much faster and gives you a tight result. So this is the first problem we're going to discuss. The second problem is what is called the Submodular-Welfare problem. So we have m elements, unsplittable elements, and k players, and each player is equipped with a utility function. And the goal is to assign elements to the players. So let's say this player I got elements 1, 3, and 4. So the revenue or the utility we get from this player the utility of the subset of elements it got. And the goal, of course, is to assign all elements to the players and maximize the social welfare or the sum of the utilities. Of course, we assume that the utilities are monotone, so the players actually compete over the elements. So nothing is, a player doesn't lose by gaining more. So the formal definition of the problem is this: you just have m unsplittable items, k monotone submodular utility functions, one for each player, and the goal is just maximize the social welfare by assigning the elements. And this problem also arises very naturally in the combinatorial auctions. This is probably one of the main reasons for considering this problem. So what is known about this problem from an algorithmic point of view? So 1/2 was known even in the late 70s using a greedy approach by Fisher, Nemhauser, and Woolsey. And actually it was reproved in 2001. They probably were not aware of this result, reproved again by Lechman et al. And what is known today, prior to the work I'm going to describe about this problem? So there's the von Trapp algorithm that achieves 1 minus 1 over E. So, and we will see this is quite close to the hardness result. And this seems quite nice, except for the annoying fact that before that there was the Dobzhinsky and Shapira algorithm, which asymptotically, if the number of players increases, is roughly 1/2. But only for the case of 2 players, it gets 2/3 approximation, which is better than this. So this seems quite annoying. Why the case of only 2 players should be better? Is it special? We don't know. So there were additional works on this problem for special objectives by Dobzhinsky and Shapira, and Feg also studied subadditive utilities, and also if you have a stronger oracle, a demand oracle. This was also studied by Uri and Jan, and so on. So there's a long list of works on this problem. And of course, the interesting question is the case that k equals 2, is it special? So this algorithm is kind of annoying in the sense that it kind of ruins the von Trapp algorithm for this special case. What is going on there? So what is known about hardness? So first of all, you might ask, why do we look at submodular utilities, not general utilities? So first of all, submodular utilities are common in economics, so it makes sense. But if you look at general utilities, then you can show that this is equivalent to set packing, and you can't hope to gain anything meaningful here. So what is known in terms of hardness for the submodular case? So there is this hardness, 1 minus 1 over k to the power of k. So first it was proved assuming p does not equal np by Kot et al. And then this assumption was actually dropped. It's not needed. You again get an absolute hardness, which is unconditional. And you can see that as k increases, it converges from something larger to 1 minus 1 over e. But for example, what happens with 2 players, it gives you only 3/4 hardness, right? So not only the case that of 2 players is interesting, there's a gap even for the Dobzhinsky and Shapira algorithm, which gives you 2/3. So what we will see in this talk is actually, what's starting from this question is you get that this is the right answer. You can get exactly this. So you can, for any number of players, you can get this approximation for the problem. Actually, this also settles the approximability of the submodular welfare problem. And the last problem I'm going to mention is what is called maximizing a submodular function over a matroid. So again, we have a matroid and a submodular function. Just want to find an independent set in the matroid that maximizes the value of the submodular function. So why is this problem interesting? First of all, it captures the submodular welfare problem. I won't go into the details, but actually the submodular welfare problem is a special case. It's a partition matroid. And also maximum coverage, generalized assignment, these extremely 2 basic problems, and also refinements of these problems and so on, all are special cases of maximizing a submodular function over a single matroid. So again, what is known about this problem? So here we have to be careful because it depends whether the function is monotone or not. So if the function is monotone, so there's the 1/2 algorithm I mentioned before. So it was proved for a general matroid, so it captured the submodular welfare problem. And then a few years ago, by Calinescu et al., it was improved to a tight 1 minus 1 over e. And the reason it is tight, and this is also quite amazing, because even in the late 70s, these guys proved an absolute hardness for this problem. They showed that if for any fixed epsilon, there is a matroid that if you get an approximation better than this, the algorithm needs an exponential number of Oracle queries. And this is kind of amazing because it was done even in the late 70s, where people it wasn't very common to prove hardness results. Of course, they didn't get the exact number, they got only 1/2. Of course, there were tons of work on special cases, and also you cannot forget to mention Uri's hardness result, which is the same, but of course it assumes P doesn't equal NP for the maximum coverage problem, because it's a special case, and there the function is actually given explicitly in a compact way by the sets themselves. So what is known for the non-monotone case? So as you can see, the numbers here are not very nice. And the reason is probably due to the algorithmic techniques you use in order to get these approximations. So the 0.3.9 was the same soda paper was improved to roughly 0.325, and even the hardness result is not very nice. And again, all these are fractional local search or extensions of local search using simulated annealing and so on, as opposed to, for example, the greedy algorithm that gives a nice result here. So again, the question is, why aren't there any nice numbers, for example, for the non-monotone case? And the answer is that there are. The only reason is that you need to know how to get them. So what we will show is that if you actually, you can extend the techniques here in quite a different way and get improved, and not only improved approximation, but also nice numbers. This also raises a few interesting questions that I might mention at the end of the talk. So these are the three problems we saw, and I'll just mention that there are additional applications. For example, the submodular Max-DiCut, where you just have a monotone submodular function defined over the clauses of a CNF formula, or you can change the Matroid constraint by a constant number of knapsack constraints. So these two problems also fall under the general framework we're going to show. So let's, a few minutes, just mention what are the algorithmic techniques that are known in this case. So as in approximation algorithms, you can use a combinatorial approach. We saw that greedy works, local search works, and in some cases, this gives you or the current best results you know, or even tight results, so you can do better. For example, a knapsack constraint, Sviridenko showed that this is tight, and the intersection of K-matroids by Lee et al., this is the best you know. And even later on, we were able to improve this result and actually show that, for example, for submodular matchings in general graph, you can match the result known for bipartite graphs. So this was open even from the late 70s. But the problem with all these techniques is that it's very tailored to the application you have. So you need to find the exact greedy rule or some local search, so it's not easy to work with all the time. So as in approximation algorithms, there's the continuous approach, where you just formulate a relaxation, find a good fractional solution, and round it. So why is this? So we were not the one to invent this approach. Actually, this is the approach that was used to obtain the tight approximation for a monotone submodular function over a single matroid by Kalinescu et al., the work I mentioned. And surprisingly, in most applications, and essentially in all the applications I mentioned in this talk, the bottleneck is actually the second step. How to compute good fractional solutions, and this we'll see it's a hard problem. So usually the rounding is not a big issue, but the issue is how to find a good fractional solution. And also this step, the second step of finding a good fractional solution, differs from the monotone and non-monotone case. And in the non-monotone case, you have very involved algorithms using simulated annealings, and then give you all these not very nice numbers as guarantees. This also was extended by Chekuri, Vondrak, and Klusen very recently. So interesting questions as we saw. Can we bridge some of the gaps? And in some cases, I told you in advance that we can. And also, can we simplify, for example, the computation of fractional solutions from non-monotone functions? Can we improve the result? Or in other words, can we get nice guarantees somehow? So what we will see in this talk, so I already told you that we will see a linear time-tight algorithm for the unconstrained problem. And we also see a simple way of computing fractional solutions. And the advantages of this method is that, first of all, it will be a single algorithm that works both for the monotone and non-monotone. So essentially, there's no distinction anymore between the two cases. It will give improved results for the monotone case and also give improved and nice results for the non-monotone case. And it's, again, everything with a single algorithm. So no need to distinguish between simulated annealing and continuous greedy and so on. And for example, as I mentioned, the few applications, immediate applications of the second step are information-typed results for submodular-welfare with any number of players, or submodular max-DiCut, or this is the guarantee we get 1 over E for the non-monotone case when this improves, for example, these two results immediately. So again, as in approximation algorithms, if you improve the solver or how you compute fractional solutions, everything improves essentially all the results. So these are just two well-studied examples. So if there are no more questions about this introduction, I'll start with the unconstrained submodular maximization problem. So first, let's see why the greedy approach fails. So why do we look at all at greedy? Because greedy was useful in the monotone case. So we saw that it gives 1/2 in the discrete setting, a greedy 1/2 approximation. Now I'm telling you that this is what is called the continuous greedy algorithm, which I'll mention at the end of the talk. So it gave tight result in the monotone setting. So let's see why it completely fails in the non-monotone case. So this is a very simple example. We have n+1 elements in the ground set. And let's say we have a v and u1 up to un. And we have an indicator function whether the subset contains v. And this function is, of course, submodular. And we have an indicator function for every ui, which says whether ui is in the subset and v is not in the subset. And this indicator function is also submodular. And the objective is just a non-negative combination of those, but we put a slightly larger weight on v's function. So what the greedy will do now, so there's nothing, and which element is best to choose? It chooses v, because it gains 1 plus epsilon. And once it chooses v, it is done. It can't gain anything more. And what the optimal solution is just choose all the u's. So there's a gap of n. So it actually means that the greedy approach is meaningless in this case, at least in the combinatorial setting. So now let's see a very, it looks very simple, yet it is extremely crucial, this observation. So let's say we have some greedy algorithm that achieves something for the unconstrained submodular optimization problem. Then we can trick it. Instead of giving the algorithm access to f, we give it value oracle access to the complement of f. So what is the complement of f? It's just the value of f on the complement of the subset we've given it. And the algorithm doesn't know that. So if the algorithm has any hope in achieving something, then why start with an empty solution, gain elements slowly? You can equivalently start with everything and start dropping elements, right? Because it's a complement of f. So this is probably why the greedy doesn't make any sense. So why it's, in a sense, very asymmetric. And note that the optimal value of the complement of f has the exact same value, and the optimum is actually the complement of the original optimum. So everything is just mirrored. And these are the two obvious questions we ask. Why start with nothing and where you can start with everything and start dropping things? So let's start with the first attempt and see if we can do something. So this is the vertices of the hypercube are the possible solutions. So let's start with two solutions. So we will have two sets, the empty one and the full one. And now let us look at the first element. Let's say this direction. So delta 1 is just the change in the value of the objective once we move this point here, which is equivalent of choosing the first element. And delta 2 is the change in the value of the function once we remove the first element. So it's moving from here to here. So now what do? We just greedily choose the best option. Let's say delta 1 was bigger, so we move this point here. Now we look at the second element, and let's say delta 2 is bigger, so we move the upper point there. And in this case, let's say delta 1 won again, and these 2 points collide, and let's say this is the output. So this is extremely simple. And this is actually the algorithm. So go make one pass over the elements, I1 to n. And this is the definition, the formal definition of delta 1, delta 2. And if delta 1 is better, then choose that element. So S just remembers what the algorithm chose so far. And if not, then removing that element means not adding it to S, so just do nothing. So this is the formal way to write the geometric interpretation you saw before with the drawing. And surprisingly, this very simple algorithm gives you 1/3 approximation. So it's not the 1/2 we want, but it's a kind of a very natural extension of the greedy approach. But in a sense, it utilizes two evolving sets and the symmetry property. Of course, this runs in linear time. And we can prove with Mohan, Feldman, and Sefino that this gives you 1/3. So how the proof goes, I'll just go over the overview of the analysis, which is not very complicated, but it will take a few minutes. So because we're not really in the greedy setting, we're not going to bound how much we gain in each step. We're actually going to see that we do not lose much. And the amount we lose will depend on how much we've gained. So when I say how much we lose, the question is lose where? So we'll lose here. So what do we have here? So let's say Si is just the elements the algorithm chose up to the end of the iteration I. And opt_I is just the elements of opt from the last n minus I elements. So these two sets are always disjoint, right? This is a subset of the first I elements, and this is a subset of the last n minus I elements. And the creature we're going to look at is Si, the union of opt_I, the union of these two. So with 0, this is just the optimum, right? We haven't done anything. And as the algorithm progresses, at the end we get to the output. So this is just an artificial creature you look at in order to analyze the algorithm. So this loses. So you start from A0 and you end it with AN, and you lose somewhere along the way. We started with opt, and you end with the algorithm, the value of the output of the algorithm. And the heart of the analysis is just to bound the loss in 2 consecutive steps of this thing. And how you bound it. So in this case, it means we chose the element. And in this case, we showed that the loss is upper bounded by delta 1, which is exactly how much we gained in this step. This is the step we did if the algorithm chose the ith element. And otherwise, we gain, again, the change in the value of the function of what the algorithm did in this case, which is not to choose the element. So when you sum everything up, you just get 1/3 approximation. Intuitively, we see that the total loss from here to here is the total change that the both points had along the entire execution of the algorithm. And this, when you look at the rates of the change, it gives you 1/3 approximation. So now let's look at a very special case. So this is just a reminder of what delta 1 and delta 2 is. So first of all, you can prove that always the sum of these two is non-negative, and you just need some other submodularity for this. So it means that at least one of the steps you will not lose. So if, let's say, the first option is beneficial and the second one is not, then of course it is obvious, at least intuitively, that we want to choose the element. And the other case where it is we lose by adding the element and gain by dropping it, then of course dropping it is equivalent to not adding it. But let's say both are beneficial. And not only, let's make the question even harder. Let's say not only both are beneficial, are of the same amount. So it's exactly the same change. So what do we do then? So like everything in life, when you have two options and they both look the same, so you just flip a coin. So what we're going to do is, in this case, where both changes are beneficial, we're going to choose randomly. And of course, the probability will be proportional to the ratio between these two, of course. So this is the algorithm. So this is exactly the same algorithm. These are the two cases as before. If the second one is non-beneficial, choose the element. If the first option is non-beneficial, then don't add it. So do nothing. But if both are beneficial, just add the element with this probability. And this is the new algorithm. And quite surprisingly, once you you turn this algorithm essentially into a random process, with this time Niv also joined the gang, you can prove that this gives you a tight 1/2 approximation. So in a sense, yes?
Or with high probability?
with expectation. So if you're okay with an expected value, it's fine. If not, you can just run it a few times. But it's highly concentrated. But this is in expectation. For example, as in Max-DiCut, the Gomez-Williamson algorithm, the value of the cut is in expectation. So it's at least one half of the optimum in expectation, and it also runs in linear time. I'm not going to go over the proof overview of this algorithm, but I will actually show what is called the continuous counterpart of this algorithm. That will also give a few intuitions on the third part of the talk, which involves fractional solution to some modular problems. So in order to define what is continuous or fractional, we need to actually extend the submodular function because it is a set function. It is defined only over the vertices of the hypercube. So now we want to define it over the entire hypercube. So we're going to use what is called the multilinear extension. So there's a huge expression here, but it has a very simple probabilistic interpretation. If you have a fractional point, it means every element has a fractional value. So define the distribution the following way. Each element chooses itself independently with this probability. This gives you a distribution over subsets. Just take the expected value of the submodular set function over this distribution. So this is exactly what is written here. So note that if x is not fractional but an integral vector, then the distribution has only one outcome with probability 1. So in this sense, it is an extension. It actually extends the function. This is not the only extension. There are other extensions which are useful in other settings, for example, the Lovász extension and so on, but I won't go into this. So this is the new objective, the multilinear extension. And what is the continuous counterpart? So I'll just show it with a picture. So again, we start with these 2 points, and we look at the change. But let's say this time both are beneficial. So instead of choosing randomly, we'll just go to some point in the middle that depends on the proportion or what actually determines the probability. So we get here and there. And now we look at the change by moving from here to here. But now look, these are actually the marginal values according to the multilinear extension, not the original submodular set function. And again, let's say this option is beneficial, so we move it here. And again, let's say both are beneficial here, so we end at some fractional point in the middle. And this is the continuous counterpart. So it's not an equivalent algorithm, but intuitively it is what you can call the continuous counterpart. So how the analysis goes here, so this is exactly the same thing that is written before, but instead of SI, we have a fractional vector that depicts what the algorithm chose, the fractional values up to the end of the ith iteration. And this is defined exactly as before. So again, this is the deterioration, and we bound the change in 2 consecutive elements. But now instead of the total movement of the points, because we are in the continuous setting or intuitively in a random process in the combinatorial setting, we bound it by the average change in the value of the points. This is exactly delta 1, and this is delta 2, and we actually bound it by the average instead of the total. And now you actually get a lower loss. It means that no matter the average, not distance, but change in value of the points that they move, is actually the amount you gained. So you actually meet in the middle, which is 1/2. And this, so formally you need the telescopic summing, but intuitively this is exactly what you get. So quite surprisingly, this is a very simple algorithm that settles the approximability of this kind of basic submodular maximization problem. And it's very simple, runs in linear time, and gives you tight results. So this finishes what... so I won't prove these things, but this is essentially the heart of the proof. In order to just define this creature and bound the loss you get with it along the execution of the algorithm. So now we've seen that continuous interpretations could be nice. Of course, there's a proof for the randomized combinatorial algorithm as well, but we've seen that actually the proof of the continuous counterpart is also quite easy. And this, and now we get to the third part, which also involves fractional solution or continuous algorithms. And as I said, we'll see how to compute better fractional solutions to submodular maximization problems. So these, just recall all the problems we have. So we settled this problem, and now we'll see actually all these applications with one shot, essentially. So the first question is how to formulate a relaxation to a submodular function, a submodular maximization problem. So we have the multilinear extension. So it's easy. Just find, as in any approximation algorithm, find a polytope in the hypercube that contains the feasible family of solutions, and just maximize the multilinear extension this time over all points in the polytope. So this is a very simple way to, once you have the multilinear extension, to formulate a relaxation. The problem is that the objective now, the multilinear extension, is not convex and it's not concave. So this usually is kind of problematic because you can't use off-the-shelf some solver or something. This function doesn't have a very nice shape, but as we will see, it has some properties that still make it possible to compute good fractional solutions, despite the fact that it's not convex and it's not concave. So let's look at what is called the continuous algorithm or continuous greedy algorithm, and this is a von Drach's algorithm. So let's say this is our polytope. So what do I mean continuous greedy? So it's greedy. We start with, let's say this dot here starts with nothing, so it's all zeros. And let's look at the marginal values of all elements. So we have element I. So the marginal value is just adding that element to the current point x and see the change in the value of the function. And again, note that we're looking now at the multilinear extension, not the original submodular set function. So we look at the marginal values according to the multilinear extension. And now once we have these weights, we can actually find the best point in the polytope that maximizes this as a linear function. So intuitively, why do we do this? Because as I'll just mention, I won't prove it, the multilinear extension extremely locally is almost linear in directions which are parallel to the axes you have. So it makes sense that if we're not going to move a lot, but just move slowly in this direction, it makes sense to find the best point in the polytope that maximizes this. So this is kind of a replacement for the gradient, in a sense. So we find y, and just we move x. We just move a small delta step size to the direction of y. And now the marginal weights are different because we're a new fractional point x. So we have a new y, and again we move a small delta step there. And again we calculate each time the new y and move each time a small step until we decide to stop. So this is the geometric interpretation of von Drach's continuous greedy algorithm. So this is so if you just want to recall the algorithm, remember this picture. It's always easier. This is the formal definition. The important thing to note here is that intuitively it is easier to think of that the algorithm runs in continuous time. So actually the time starts with 0 and then delta, 2 delta, 3 delta until we stop. So it will be easy to talk about time when running the algorithm. And as we said, each time compute the marginal values according to multilinear extension, find the best point in the polytope, move in that direction and update the time and do this. Of course, we stop at time 1 because we are guaranteed then to have a convex combination of points in the polytope, right? And if we have a convex combination, then we are feasible. So this guarantees we have a feasible solution. So as we said, it is convenient to think of the time as moving in jumps of delta. It gives a combination, and it was first proposed by von Drach in the context of the Submodular-Welfare problem. So what did von Drach prove? So this is not exactly the original statement, but it can be written this way, and it will be convenient in our setting. So if f is monotone, and p is down monotone, so what do I mean that the polytope is down monotone? So since we are in a maximization problem, this is essentially a packing problem, right? So you can always choose less and still be feasible because the objective is to maximize something. So this is what I mean by a down monotone polytope. Then if you terminate the algorithm at time t, you get a feasible solution whose value is at least 1 minus e to the power of minus t times the optimal value. You get a fractional solution.
So this is true exactly no matter what delta is?
So I'm hiding some of the details because you can't choose delta 1. Delta needs to be small enough. And there are also minus little o of 1's losses here. And in some cases, the little o of 1 losses can be omitted. So there are additional tricks. For example, in the case of Matroid, they can be omitted, for example. For the knapsack constraints, we don't know if they can be omitted. But I think, for example, in the Matroid setting, it's enough to choose 1 over n square or 1 over n cube. I don't remember exactly as delta. So it's not like 2 to the minus n. So it's a small polynomial size, but it's not extremely small. So that will be enough. So I didn't tell in the beginning of the talk, so some of the details I'm hiding and shoving under the rug. So as long as you don't ask questions, they will be hidden there. So, so here, yes.
So your multilinear extension is a function of R.
Yes.
The subset R. How do you?
What do you mean subset of the hypercube?
I see.
Essentially, yes. So you need to be contained in the hypercube, otherwise it doesn't have any meaning.
So R is the hypercube. Is that what it is?
No, I didn't say
It's
that.
a random set.
It's a random set. I see. So you
Oh yeah, you mean when I've written the multilinear? Yeah, R is just summing over all. It's not the calligraphic R. Maybe it's not the right choice of notation. Yeah, but it means that R is the random set according to the distribution defined by the fractional values, as I described before. So there are a lot of technical details here, but essentially this is what it means. And the problem is that this fails for non-monotone functions. So the fact that f is monotone here is important. And as I said before, Chekur et al. Gave ways to solve the multilinear relaxation we saw for non-monotone cases, but there you use simulated annealing techniques and you don't get nice guarantees, nice numbers, I mean. So let's look at, again, the solution where I'm going to show is extremely simple. So let's see what's going on here. So the algorithm at each step chooses the marginal values according to the multilinear relaxation. These are the weights. And it maximizes, find the best point in the polytope according to these weights as a linear objective. So where is the monotonicity used in the proof at all? Right? If it's not used there, it should work also for non-monotone functions. So the only place it is used is just to show that the marginal weights, marginal values are upper bounded by the derivative, the partial derivative in the direction we're looking at. And why is this true? Because the function is monotone, so the multilinear extension is also monotone. So this is non-negative, and once you divide by this, then you can only increase it. There are no negative numbers here. And of course, you can divide by this because if you fix all coordinates and just change one coordinate, the function is linear, essentially. This is what is called the multilinear extension. So I haven't proved it, but it's like one-line proof. So because the derivative is linear, it behaves like this. So the question is, can we do better? So what is actually going on here is that intuitively we would like to use the derivative, the gradient, it's not the marginal values. So how can we correct this? So we know that the marginal value is actually the derivative times 1 minus xi, because if we position xi, this is just because it is linear. It is multilinear, so we're just going to change the update state. Right? We're going, instead of adding delta times y in the coordinate of I, we're going to correct this in order to mimic the effect of the gradient or the derivative. So this seems quite intuitive enough, and this is essentially the algorithm we get now. This is the only change. So this might look like only a technical change we're doing to the algorithm, but remarkably, it has a very deep effect. So what we can prove with, again, this is with Mohan and Sefi, that once we do this tiny change with the algorithm, so first of all, the algorithm works also for non-monotone objectives as well. And we can prove the following. So if you terminate the algorithm at time t, if you're not monotone, you have this guarantee, and if you're monotone, you have this guarantee. 1 minus e to the power of minus t as before. So this is kind of surprising because it tells you that the original continuous greedy, the von Drach's algorithm, is kind of wasteful, or the step size there is wasteful. Why? Because even in the monotone case, the more you gain, the more value you can have, because everything is monotone, right? And we do actually smaller steps. We move physically less the point because we have this correction factor, but the rate in which we gain in the value of the solution is exactly the same. So we move less and gain the same. So it essentially means that there is something wasteful in the original algorithm, then probably the right way to correct it is what we did. And this, of course, in a very straightforward way. I'm not sure time will permit me to show the overview of the proof for the non-monotone case. You can actually prove that it starts working in the non-monotone setting as well. So let's see now. So this is the guarantee we have. So what happens in the non-monotone case? So we know that if we stop at time t, we get t times e to the power of minus t. So the best t is t equals 1, right? This maximum, you get 1 over e. And if t is 1, then we are guaranteed to be feasible. Why? Because we're dominated by a convex combination, essentially. And if we stop at t equals 1, we get a convex combination. So we're dominated by a feasible solution, and the polytope is down monotone. So we're still feasible. We're something less than a convex combination. So this is fine. And note that this is kind of surprising because earlier in the talk I showed you that the greedy approach fails for non-monotone functions. So if it fails for the unconstrained case, of course it fails for all the constrained cases. But there the subtle difference was that we were in the combinatorial setting. So once we look at the greedy approach in the continuous setting, with the right algorithm, it actually works. So this is probably why it wasn't examined before, because people knew that the greedy fails for non-monotone functions. But the point is it fails only in the greedy setting for non-monotone functions. In the combinatorial setting, yeah, sorry. So what is going now in the monotone case? So here the situation is a little bit tricky. So as I told you all, so that gives the 1 over e for the non-monotone applications, but what about the Submodular-Welfare problem or the Submodular Maxat? I said that we improved the results and got something tight. So how do we do this? So again, we gain at the same rate, and here we wish to end at the latest time we can, because the larger t is, the better we are, right? The more we execute the algorithm, because it's monotone, the more we gain, the better solution we have. So the key insight here is that we advance less when you compare it to the original continuous greedy algorithm, because we do smaller steps. So the obvious question is, can we stop at times which are greater than 1 and still be feasible? So intuitively, this means that the previous algorithm would actually go out of the polytope. That would essentially what will happen, because it will be more than a convex combination. But here we gain less, and can we stop at a later time and gain here in the value? But the situation is a little bit tricky because the correction factor is different for each element, and it's different at each step. So it's not clear. And apparently the property that dominates the time, or can help you choose the optimal stopping time, depends on what you might call the density of the polytope. So the polytope is just a pecking polytope. So all these are non-negative. We have, let's say, m constraints, and all that some non-negative combination of variables, at most some non-negative number. It's all pecking constraints. So what is the worst constraint? So for each constraint, we can look at the right-hand coefficient divided by the coefficients of the variables. Don't forget that these are all 0, 1. Either you choose something or you don't. So the most constraining or the most constraining constraint in the polytope is the one that minimizes this ratio. And this is what you might call the density of the polytope. And you actually can prove, no matter how the algorithm does the steps, that you can, the solution is feasible as long as the stopping time is this expression that depends on the density of the polytope. And this, when you plug this in the result, you actually get this approximation. So what happens now, for example, for the Submodular-Welfare with 2 players? So in this case, the density of the polytope is just 1/2, because all the constraints are that each element can go to one of 2 players. So when you model the problem as a Matroid, you just give each element in the welfare problem, 2 elements in the ground set, 2 copies, one for the first player and one for the second player, and just want to distribute them. So when you look at all the applications, for example, so that's for 2 players, but if you have k players, you get 1 over k, and this gives you exactly information-theoretic tight results. For the welfare problem with k players for any k and Submodular Maxat, and as I said before, for the non-monotone cases, it gives you a nice guarantee of 1 over e. So I didn't mention, so as I said before, usually the heart of the problem in these type of of questions is how to find good fractional solutions. The rounding is not an issue here. There's the given Sviridenko, or what is called the pipage method, to rounding solutions, fractional solutions over a matroid, so you don't lose anything. Here I'm lying a little bit. In the case of knapsack constraints, you lose some epsilon. So because if you put a linear objective, it's like getting an optimal solution. So there's the epsilon of the f betas here. But these are all just technical details. So the surprising thing is that with a very simple and probably correct change of the algorithm, we can make it work also for the non-monotone setting and get all these information theoretic tight results quite simply. So I guess I don't have time for the proof overview of the non-monotone case. I'll just tell you the phases of the proof. It's not very complicated. So if x is the current position of the algorithm and y is the direction we move at, so the first step is to show that, so this actually means the change or how much we gained by doing one step from time t to time t plus delta. And we show that we gain, so delta is, of course, it's linear, but we gain something that depends on if you move in the direction of up. So if you're currently in this position and you would have moved to the direction of up, this is how much you would have gained. But we moved to better direction, which is the best one, and so on. So we proved this, and these are where all the little O1 terms come from. And then we just bound this, and here we actually use the Lovaas extension, which is really nice, and then you obtain a recursive formula and you're done. So the proof is not extremely complicated. So short proofs is always nice if you have them. So this is roughly the proof. So let's just wrap things up. So what did we see? So the first thing we saw that just this very simple symmetry observation and the fact that we can have two evolving sets gives you a tight linear time algorithm that essentially resolves the approximability of the unconstrained submodular maximization problem. And also we saw that essentially there's no computational difference between non-monotone and monotone objectives in the fractional setting or in the continuous setting. So there's no need to distinct. The proof was, of course, is different, but the algorithm is the same algorithm. And essentially, the bottom line is that greedy does work for non-monotone objectives, but it only works in the continuous setting and not in the discrete setting. There are, of course, tons of open questions and ongoing projects. So the first open question is whether the 1 over e the right answer now for computing fractional with the non-monotone objective. So this is the first time there's a nice number. And it's better than all the, so it's not only a nice number, but it's better than the previous not nice numbers. So the question is whether this is tight. And remember that the hardness result for a single matroid, for example, is this 0.498 something, which is also very interesting because it took a lot of time to get a hardness which is below 1/2, the Vondrak paper. So we have no idea whether this is tight. We've tried a little bit, but we don't know. So this is a very interesting important question, and we essentially say what you can do over a single matroid, because in the rounding there you don't lose anything. So, and also several other projects that use ideas I mentioned in this talk. So I mentioned also maximization over the intersection of k-matroids. So this captures like k-set packing, k-dimensional matching, and so on. The problem is that the techniques that are known for these types of problems are all combinatorial and all local search. And there are gaps even in the linear objective case, so not only the submodular setting. So this problem is still open in the usual sense of approximations. And we don't know whether continuous tools work here. And here the problem, so we can get a fractional solution, but this time the rounding doesn't work well. So it's not a single matroid. So even for k equals 2, there's a gap. We don't know how to close it. So two other important questions is, for example, can techniques used here be used for problems which are not submodular? So I mentioned Max-DiCut a few times, and also Generalized-Assignment, which is a special case of the Matroid constraint. So we have a few intuitions, and probably once I go back home, this is one of the things we're going to start doing. So can we actually improve one of these two basic problems using the continuous techniques, or even the symmetry properties that are also that we saw in the unconstrained problem are also there in the Max-DiCut problem, the usual Max-DiCut. So can we use this to get better results? And also another interesting problem, and there is some advancement on this from 2 or 3 weeks ago. So we've talked about matroids, but what happens about bases of matroids? So even if you look at a uniform matroid and say you want to choose half the elements, so this captures maximum bisection, maximum directed bisection in graphs. And apparently, so we know that the continuous greedy can work in the non-monotone setting. However, you don't get a convex combination of points. You get something less. And doing this small jump from something that is dominated by convex combination to a convex combination, we want a base and not an independent set, might cost you a lot. And it can't be done. So actually, we use symmetry properties here. So we have improved results on these. But the general problem, only for a uniform matroid, but the general matroid, we don't know yet what to do there. So this is a partial list of, I hope, interesting problems. And thank you. This is it.
First off, I think those are very impressive results.
Oh, thank you.
And also, I think for me, the algorithm, the continuous algorithm you demonstrated, I think it's Frank Wolf, right? You know Frank Wolf algorithm?
No.
If you look, it's precisely
so this
almost exactly that. Is that the only difference is that you use fx with 1 minus f. It's kind of increment. It's approximate of the gradient.
So you mean it uses marginal values instead of the gradient or the derivatives?
Yeah. It's in the Frank Wolf algorithm. It's kind of in the 50s invented for continuous optimization, and it's exactly that framework. If you look at it, I can point.
So, but it was in the context of linear objectives or any
non-linear objective with precisely with the bounded polyhedral.
Yeah, but the point so it might be related to this, but the point here, for example, Vondrach's proof. So he was the one who suggested the continuous greedy in the monotone setting, was to show that this works with the non-linear objectives. The objective there is also not convex, not concave. It's the multilinear extension. So it might be the same algorithm, but for example, I guess that Vondrach's proof is quite different because the objective has completely different shape.
The proof, I'm just saying the algorithm looks like.
Oh, actually, it's a very simple, very natural suggestion. So
very natural suggestion.
Yes, so it's not surprising that it was used, a few times.
And recently, it was in the learning community of signal processing with greedy approximation. People have some. It's also people rediscover that this is also Frank Wolf. So it will be interesting.
So it's like regret minimization. You discover again and again and again.
No, I think
like in all the different
I certainly know that the proofs of what is the complex
so
result
here
is non-trivial.
Oh.
It's just that's I believe is something. But I just point out that the algorithm framework looks like this one.
So essentially, if you get an algorithm that is conceptually simple, and you can prove something, that is always better. So if you have simple solutions that work, of course, that's always better. Any other questions?
Thanks.
Okay, thank you.